Okay, let's go ahead and get started. Welcome to day 9 of Organometallics. So today we'll be marching forward and building on this theme of putting together all of the elementary steps that we've studied in a fair amount of detail over the past couple classes. And stringing them together into catalytic cycles that then become useful in organic synthesis. And so we'll start with what might seem like review for many people, but I think it's important to go through and define key terms and define key principles so that everybody is really on the same page. And maybe even if you've seen this type of treatment before, seeing it again might allow you to pick up something new that you haven't seen or haven't appreciated previously. And so we'll start out talking about general principles of catalysis as they pertain to organometallic chemistry, and then we'll move into some more specifics of how to think about these in terms of asymmetric catalysis. And this will become an important, some of these principles will become important when we start talking about hydrogenation in particular. And then we'll conclude by talking about ligand design principles. So one of the themes for today will be the fact that chemists have this ability, at least in the realm of homogeneous catalysis, to really tune the three-dimensional environment around the active site of metal catalysts. And then it's important to know what the underlying principles are there. Okay, so let's get started. I'm sure everybody here has seen this definition before, but again, just to refresh your memory, a catalyst is any substance that increases the rate of a chemical reaction without itself being consumed. It was defined in these terms by Oswald at the end of the 19th century. And so for us, in the context of this class and organometallics, basically this means that at the end of some multi-step sequence, the complex of interest needs to get back to its parent state one way or another to be able to serve as a catalyst. So if there's an oxidation state, for example, that one of the steps is reductive elimination, then you need to get back to the parent oxidation state of the catalyst to be able to turn over. And so, again, one of the points that we made earlier in the class is the distinction between kinetics and thermodynamics. We'll keep coming back to this again and again. So a catalyst does not in any way change the thermodynamics of a chemical reaction. So this hypothetical A plus B goes to C plus D reaction. The thermodynamic parameters are determined by the connectivity of the starting materials involved, as well as by things like concentration, etc. But the kinetics of the reaction, how quickly the reaction goes, whether it's feasible to take place at the reaction temperature, those are determined by the activation barriers, and that's where involvement of a catalyst. So typically the catalyst is going to coordinate to the starting materials, coordinate to facilitate formation of some kind of intermediate, and then dissociate to the product. And so the overall effect is that this will lower the activation barrier. So these are the key factors that are changed by the catalyst, delta H double dagger, delta S double dagger, delta G double dagger. And then this is a little confusing, but so big K here refers to the equilibrium constant, and then little k refers to the rate constant. And I couldn't think of a good way to distinguish which is which, so I just tried to draw them in really exaggerated form. So capital K, when you read papers, capital K is equilibrium constant, lowercase k is rate constant. I'm sure you've seen this before anyway. And then one of the key points that is brought up in the Hartwood textbook, at least, is the notion that the catalyst, you have to, in thinking about how the catalyst is promoting or not promoting the reaction, you have to think about how it's potentially stabilizing or destabilizing the ground state, and then how it's stabilizing or destabilizing the transition state. so, again, if you bind a catalyst to A and B here, then the ground state is going to change. So you'll have another intermediate on this reaction coordinate, and if that's more stable, potentially you have a higher activation barrier depending on how it stabilizes the transition state. So typically there are some hidden steps here with metal catalysts where A and or B can coordinate to the metal, and there's then another intermediate that needs to be accessed along the reaction coordinate. And so let's just consider a hypothetical catalytic cycle. I think one of the things that is, and so this is straight out of the Hartwig textbook, I think one of the things that's nice about the presentation here is that it is not only an idealized form of a catalytic cycle, but it also considers what you often encounter in reaction development or when you're applying catalysis and organic synthesis, which is the various deactivation pathways and having to think about how to get things, quote unquote, get things to work when they're not working. And so typically, a catalytic process that we're going to use in organic synthesis has some combination of catalyst precursors, and these are things that are always listed above the reaction arrow. And typically the active catalyst is not what you throw into the flask. For example, any nickel catalyzed reaction that's using nickel cod. Nickel cod is rarely the active catalyst. It typically needs to associate one or more ligands and potentially adjust its reaction, its oxidation state. And so then there's some process of activation that happens to get the metal on cycle. And then what can often happen is that when you're using your ancillary ligand in excess, then sometimes you can have situations where additional equivalents of the ligand coordinate, and these can pull the catalyst to an off-cycle reservoir. This can actually be beneficial because sometimes it can stabilize a catalyst from precipitation as nanoparticle or something like that. But this would then potentially be factored into the overall rate expression. So the active catalyst then can bind a substrate molecule. Here there's another possibility for deactivation. And so the example that they give in the Harvard textbook is that this could potentially dimerize and be off-cycle, as shown here. And then there's going to be some reaction that takes place. In this case, it's depicted as a unimolecular reaction where the substrate's transformed to some intermediate bound to the metal. Here, too, there's another opportunity for deactivation. And in this case, the deactivation is shown as being irreversible. So this could be something like, for example, if you have migratory insertion and then you make an alkyl metal species that undergoes beta hydride elimination and gives you something a nickel or palladium hydride that is then an equivalent to a reduced form of catalyst, and that could be off-cycle potentially. So then the final step will be further transformation to some catalyst-bound product, dissociation of the product, and then the process can turn over. And so some of the defining features that you'll see quoted in the literature are turnover number, turnover frequency. The definitions here are very simple. The turnover number is just defined as the moles of product that are produced from the moles of catalyst. So for example, if you have a reaction that gives 50% product and you put in 10 mole percent catalyst, then that's 5 turnovers. And then turnover frequency is just the turnover number is divided by some unit of time. So one of the things that is important to think about and be precise about, particularly when you're writing papers, is when you use vague phrases like more reactive, this catalyst is more reactive than this catalyst, what does that mean? Does that mean kinetically more reactive, which is a TOF measurement, or does that mean that it has increased stability and higher TON, even though the TOF is the same? And so I think that these are things, so just to clarify that, so you could imagine, what does more reactive mean? So more reactive kinetically means an initial rate of from here to here. More reactive in terms of stability could mean that catalyst that might die like this, that can keep going for longer to get higher turnover. So this is kinetic. This is more turnover. And when you're writing papers, that's important to specify. And then a few more definitions that I think it's important to have clear in our mind. And so the Hartwig textbook really emphasizes clear definitions of some of these kinetic features of catalytic cycles. So I'll just sort of present what's presented there, and then provide a little bit more context. And so when a multi-step catalytic cycle reaches steady state, and then the net rates of each of the individual steps are identical. And so it's technically incorrect to say that there's a fast step or a slow step in a catalytic cycle. All of the steps are happening at the same rate. And so in the Hartwig textbook, they prefer this defining, this definition of a step that's turnover limiting, meaning it's the step that is sort of controlling how fast the rate is going, and that's the step that has the smallest pseudo first-order rate constant. So even though the rates of all the steps are the same, the rate constant's different, and the overall sort of the theoretical limit of the rate is essentially the rate constant of the slow step times the catalyst times the concentration of the catalyst times the concentration of the reagents. So I think that often in the literature you'll see people say this is the slow step, this is the rate determining step, and they're just using that interchangeably to mean the same thing as the turnover limiting step. But in the textbook that we're using for the class, this is the preferred nomenclature. And I think actually in terms of being clear in one's thinking, it's a little bit easier to think, more precise to think in these terms. Okay, so most of the class we're going to focus on homogeneous metal-catalyzed processes, but of course heterogeneous catalysis is a massively important area of research as well. I think reactions like the Haber-Bosch process, for example, support essentially all of modern society, and those are heterogeneous reactions. But I think homogeneous reactions are a little bit more straightforward in some ways to study and use as a platform for learning. So that's the focus of not only the textbook but the class. And so, generally speaking, there are some advantages and disadvantages of both. Some of these are probably obvious. Homogeneous processes are typically more selective, and I think that the really key point is that the reaction outcomes can be tuned through thinking about the coordination environment around the metal, the 3D geometry of the ligands, the electronic and steric properties of the ligands, in ways that is hard to recapitulate in heterogeneous catalysis. So there are people who, of course, study ligands for heterogeneous nanoparticles, for example. Frank Glorious' group has done nice work in this area, but this is still an emerging topic. So in general, homogeneous reactions are more tunable. One of the key breakthroughs in this sense was Wilkinson's use of triphenylphosphine in the 1960s for hydrogenation. And sort of that was the first system where homogeneous process had really reached the reactivity and selectivity levels that had been seen in heterogeneous catalysis. And then also homogeneous processes in general, it's easier to study their reaction mechanism. An obvious disadvantage is separation, because all of the reactions are in the same phase. It's harder to remove the catalyst and also harder to reuse. Heterogeneous processes tend to be cheaper. They tend to have better overall reactivity in terms of TON. but the disadvantages are that they're less selective, they're harder to tune, they're harder to rationally design, and that the rates compared to corresponding homogeneous processing tend to be slower. There's quite a bit of variability here, so this is just a general statement. I'm aware there are some counterexamples. Okay, so this brief introduction will set us up to think about problem of the day number 1 on the worksheet. So let's turn to that. So this problem asks us to consider a nickel-catalyzed ether hydrogenation method reported by the Hartwig Laboratory a few years ago. And they have several different protocols for this reaction, but this is one specific protocol. And so the problem asks you to propose one or more experiments that would allow you to deduce whether the process is homogeneous or heterogeneous. So think about it for a minute or two, discuss it with your neighbor. I think there are a bunch of different things you could do, so there's not just one right answer for this. So let's try to get as many on the board as we can.
Carrie?
Yes.
What's the reductant in this reaction?
Oh, sorry. That would help. It's hydrogen.
So it's the best reaction.
Yeah, sorry about that. All right, why don't we discuss some ideas here? I will mix this up so everybody gets a chance. I know many people are eager, buried at the bottom. Shao-Chun. What do you think?
Can add the mercury and to test whether the reaction is slowed down. And if the reaction is slowed down, so it's a heterogeneous reaction. Heterogeneous, and if the reaction is slowed down, it's homogeneous.
Okay. Very good. Shao-Chun is proposing a mercury drop experiment. You add a drop of metallic mercury, which is not going to be homogeneous in metaxylenes, and he says if the reaction slows down or stops, then it's likely to be heterogeneous. If it continues, it's likely to be homogeneous. So it's known that metallic mercury can can interfere with heterogeneous particulates in solution, but does not do the same thing with homogeneous processes. So that's a classical experiment. Okay, very good. What else? Oh, I'll call on Luke. Do you have any other ideas?
We try to observe intermediates by NMR to see if there's solubility. You couldn't see catalyst.
Trying to observe organic intermediates or organometallic species, or what are you thinking?
Not sure, actually.
Okay. Yeah.
This may sound stupid, but can you just filter the reaction and take the filtrate, do an ICP test, see if there's any metals in it?
Okay, so do filtration. So run the reaction, filter it. You have to make sure you have initiate the reaction, filter it. You have to make sure, depending on what you want to, how big the particles you want to remove are, that you have an appropriate filter for the job, and then do analysis. Okay.
You could also just take that filtrate and subject it to the reaction conditions as well.
Okay.
Or just use ready nickel to see if the reaction works.
Okay. Use another nickel
Simpler
source.
than
Okay. Yeah, you had another proposal, another idea tucked in there, which is to do some kind of electron microscopy. I think actually the more common is TEM. Here you'd be looking for nanoparticles.
You could also independently prepare nickel nanoparticles and subject those to reaction conditions.
Yes, you could. Yeah, I think if you first you need to know whether you're making nanoparticles, and if you know that you're making them, then you can prepare them and then resubject them to the reaction conditions.
Because you could still be making nanoparticles, they're just not.
Sure. Right. You can make nanoparticles when they're active. Any other ideas?
synthesize TME, DA, nickel, NOx metal complex, expose it to reaction conditions, and see if you get product or some sort of productive elimination.
Okay, so propose an organometallic intermediate on the homogeneous cycle, proposed homogeneous cycle, and see whether it's catalytically competent. Yeah, some kind of organometallic synthesis solution.
Dynamic light scattering,
Okay, what do you think? What are you thinking there?
like looking for Brownian motion.
Okay. Yeah, I'd have to think about that and what complications might arise, but might be possible. Okay, let's. Does anyone else want to throw one or two? Okay, so let's just go through a few others. It's good. So I think in the actual paper, the Hartwig Laboratory, with their collaborators at the Molecular Foundry, they do a mercury drop test, and then they do some TEM imaging, and both of those are consistent with the heterogeneous process. They have a complementary version of this with a NHC ligand in solution that is homogeneous. So these are good experiments. There's a complement to the mercury drop test, which is not as commonly used. To add this dibenzocyclooctatetraene. So this is like the equivalent of a mercury drop, but for homogeneous. catalysts. And then another diagnostic feature of heterogeneous processes are reaction kinetics. So sometimes, so if you're considering concentration of starting material, you can see some sigmoidal behavior where there's some clear activation period where the nanoparticles or the heterogeneous phase needs to form. And then there's another experiment that is a little bit similar to these two. It's called the three-phase test. And our senior colleague, Julius Riebeck, has done really important work using this for interrogating reaction intermediates. The idea here is that if you consider a substrate that is bound to a polymer, and then in the case where you have a heterogeneous catalyst, now you have a three-phase system where the starting material phase and the catalyst phase and the solution phase are all different, and those reactions in that scenario go very slowly. So if you can immobilize a substrate and then subject it to the reaction conditions, goes very, very slowly, that's a sign that the catalyst is heterogeneous. Okay, very good. So let's keep moving forward. So today I'll mostly just talk about some of the, in terms of asymmetric catalysis, talk about the underlying principles, and then I think we'll see these emerge, and some of these points I'll make today will become clear when we consider the specific examples of hydrogenation next class. Just so that everyone's on the same page, a molecule or functional group that's referred to as prochiral, this just means that something that upon reaction becomes a chiral center, so that can be an alkene that becomes chiral upon nucleometallation, for example. It could be two methyl groups that become chiral upon methyl CH activation. But in general, asymmetric catalysis is dealing with conversion of prochiral starting materials to chiral enantiomer-enriched products. And so there's another, I guess, important point to be precise with as you're writing papers and as you're progressing through graduate school is the distinction between chiral and non-racemic. So a molecule can be chiral, but that does not mean that it is enantiomer-enriched or non-racemic. And so a product can be a process that produces a chiral product, but that does not necessarily mean it produces an enantiomer-enriched product. And so it's very important to use this terminology in a precise way, especially in writing manuscripts. So terminology that you'll see in the literature is this rephase versus psi-phase. And this can be a little bit confusing at first. I think some people think that rephase always gets converted to R product, psi-phase always gets converted to S product, but that's not necessarily the case depending on the group that you're introducing. So the re and psi-phase just refer to considering a planar molecule and then assigning the priorities based on the standard Kahn, Engle, Prelog priority convention. And then after you've done that, the face where the priority proceeds counterclockwise is the psi phase. And so addition from that phase, and so this is coming into the board is a psi phase attack, and then coming up into the board is a rephase attack. And then some other metrics or descriptors that you've seen many times before, and I took the time to write them out just because I want to make one point about the origins of the use of EE. So in the historically, the most common descriptor of stereoselectivity in a catalytic asymmetric reaction. So for example, in some of the early sharpless directed epoxidation chemistry would be optical purity. And the way that experiment is done is that you get the pure product, and the product is a mixture of the two enantiomers in question. You measure the optical rotation, and then you compare to the optical rotation of a standard. The standard is a single enantiomer. And then the ratio of those optical rotation measurements is the so-called enantiomeric excess. And so the enantiomeric excess is defined here. Basically, the difference in the quantity of the two enantiomers divided by the total amount of the two enantiomers times 100. And so because historically this was the best measurement that could be done to determine stereoselectivity, EE, enantiomeric excess, became the standard by which the literature referred to these types of reactions. But nowadays, we actually just measure the enantiomeric ratio directly by chiral SFC or chiral HPLC. And many people prefer reporting ER because the ER directly ties into a energy measurement. So if you, for example, do a Hammett plot of the natural log of the ER values across a set of substrates, and that allows you to directly read out the energy of the energy difference in the transition state. Transition states, sorry. And then another metric that you'll see is this S value, which is the selectivity factor for kinetic resolutions. And so kinetic resolution basically takes a chiral racemic mixture and selectively reacts off one of the two enantiomers, and then you get an enantiomer-enriched product, an enantiomer-enriched starting material. And this formula here allows you to calculate the S value, S factor, which is what you report for those types of reactions. And then for some helpful rules of thumb, just to think about the energies involved in different levels of selectivity. These are commonly quoted, so some of you may have seen these before. About 1.4 kcals per mole is the transition state energy difference for a reaction that would proceed to give 80% EE, approximately 2 kcals per mole. This is the difference for a process that would give 90% EE. So the energies involved, and this is at room temperature, the energies involved are really quite modest in the grand scheme of things, and so that's one of the things I've always found puzzling as someone who works in this area, is people get really fixated on the difference between 85% EE and 90% EE, despite the fact that there's only 0.3 kcal per mole difference between those two processes. I think I'll start right over here. Okay, so now I'm just quickly going to describe sort of two general types of catalytic asymmetric reactions that you're likely to encounter at some point in your career. And without getting into all of the nitty-gritty details of the kinetics and the thermodynamics of these processes, I'll just try to paint a picture of how you can think about these, and hopefully this is useful for people in the department who are working on asymmetric catalysis especially. The first type will be reactions that involve only a single Nantier-determining step. These are by far the simplest systems that you'll encounter. Diagram. Uncatalyzed process. Let's look at this. And so, as I said, these are sort of the simplest systems where you only have essentially one step to consider. There's no substrate bound. There's no substrate-bound organometallic intermediates, where it's important to consider their transition state, their ground state energies, for example. And so a representative example of this would just be the oxidation, an anti-selective oxidation of sulfides, which can be done in these sorts of metal saline complexes as one representative example. And then this general point that I'll make up here, which is that in this subtype and the next subtype you'll see, and this I think is really important to always have in your mind when you're working in asymmetric catalysis, is that an anti-selection an antiodetermining step, or the stereochemistry determining step, whatever language you want to use. This takes place at the first irreversible step with the diastereomers that takes place via diastereomeric transition state. So basically what this says is that if, for example, you're working on a CH activation process, an anti-selective CH activation process, and CH activation is not the slow step in the cycle, then your selectivity determining step is actually not CH activation, even if that's the step where you're creating the new chiral center. The stereochemistry determining step is the one that takes place downstream, like oxidative addition to a plug-in 3 or 4 intermediate, or reductive elimination from that intermediate. And so this is important to always have in the back of your mind when you're thinking about what you can do to improve the EE. You might not even be focused on the right step psychologically. And so this is important to be straight with your thinking on. And then also, I think it's one of the reasons why mechanistic interrogation can be so powerful in the context of asymmetric chemistry. And so the other situation that we'll consider is maybe the more common one, which is reactions with reversibility prior to the enantiodetermining step. These are reactions where you've probably heard the Curtain-Hammett principle as it pertains to asymmetric catalysis. These are systems where Curtain-Hammett control can become operative. So they're certainly more complicated. And so there are let's consider two scenarios here. So let's consider a general reaction that's going to be some alkene asymmetric functionalization. And so the first scenario would be one in which the interconversion alkene-bound metal intermediates, which are diastereomers, is slow. Relative to rates of conversion. And basically what happens here is that the alkene binding step ends up being selectivity determining. First, the reaction would just start with your generic alkene, not bound to the metal. The metal is just solvent bound. And also bound to the chiral ligand. And then what can happen is it can go one of two ways. And so it can go two ways to make two different intermediates, and each of those processes has has its own transition state. Second case. And then the key point here is that once you've done this initial selection step between the two pi faces, it's all downhill from here. So this initial coordination step you see is irreversible. Once the system gets here, it's higher energy to go back and interconvert than it is to proceed on to product. And so this proceeds on to And then the second scenario, let's see here. So this is still fairly straightforward, I think. The second scenario is where the energy barriers are different such that the interconversion is significantly faster than reactions to form products. And in this case, this is said to be under Curtain-Hammett control. So probably everyone's learned about Curtain-Hammett principle, but essentially it states that in a system with rapidly converting intermediates, the product ratios are determined by the heights of the highest energy barriers that lead to the two products. So you don't need to take into account, well, you take into account, but the final product outcome is not determined by the stability of intermediates. It's determined by the barriers to get to the product. So let me draw this out. And the intermediates are going to look the same, so I'm just going to draw them in color-coded form rather than redraw. So in the end, this process is going to be determined by this barrier. The difference between those two barriers. G1 double dagger minus G2 double dagger. And that barrier, if you think about it, actually takes into account the stability of the intermediates. So that is a factor. It's not that it doesn't matter. So here's the delta G difference between intermediates. So these are the two intermediates. These are the difference between their stabilities. And then this is So now just to walk us back, to walk everyone back through it with this specific example. So now the metal is still binding to the alkene, but this is happening rapidly, quickly, and these two are in equilibrium. So the red one, as I've shown here, is more stable. So let's say this is existing in 9-to-1 ratio with the green one. But the fact that it's more stable is not what determines that it's a favored product. What determines that it's a favored product is that after it binds to form here, then the subsequent steps are lower in energy than the subsequent steps from this intermediate. And so these are the two sort of general regimes that you can find yourself in. And so I think it's important, again, when you're designing new processes, to think about what step is actually going to be an enantiodetermining and whether the reaction is going to be under Curtain-Hammett control or not. Okay, so with the remainder of the time today, we'll talk about the two most common ligands used in catalysis, which are phosphines and heterocyclic carbenes. Probably another class that's maybe equally commonly used would be CP ligands, but suffice to say, we'll focus on phosphines and NHCs today. And so we had a quick primer on phosphines when we discussed bonding and back bonding. And so now we're just going to revisit this with a bit more of a detailed treatment, specifically focused on factors that are going to be relevant to catalysis. One of the key features that underlies the strong bonding between phosphines and transition metals is the strong soft-soft matching. So this contrasts to the scenario with amines, for example, which are in the same column but are much smaller and much harder in nature, so they form weaker interactions with most transition metals. And phosphine ligand coordination can dramatically affect the properties of the metal center. Often in terms of methods development, this manifests itself as like a reaction working versus not working when you use one ligand versus another. And so a common class of phosphine ligands are bidentate ligands. And here an important descriptor is the bite angle. So bite angle refers to, in a bidentate ligand, it's this angle here. And so you can measure this directly, for example, but if you have X-ray crystal structure, you can predict it. If you have a DFT energy minimized structure. There's also something called so-called natural bite angle, which just takes into account the ligand-based preferred orientation without considering the metal orbitals, and that's just based on molecular mechanics calculation. But bite angle can vary a lot between different ligands. So let's consider these two cases. DPPE, I'll draw the structures. In case anybody hasn't seen them before, it's 90 degrees, so this is essentially like one vertex and one square, and then xanthos, it can be as large as 108 degrees. And xanthos falls within a special family of ligands, which are so-called trans-spanning ligands. Bidentate ligands can come in two flavors. And it really depends on the distance and angle between the two coordinating groups. It can either be trans-spanning or cis-spanning, which was most of the known bidentate ligands up until maybe 30 years ago, and then these trans-spanning ligands, which can actually wrap all the way around. So as I've drawn it here, at least it's cis-spanning, but it can also be trans-spanning. Depends on the metal, depends on the other ligands involved, xanthos specifically. And so one of the key trends for catalysis is that wide bite angles tend to promote reductive elimination. Phosphines can be chiral at phosphorus. So this is different than the case with nitrogen, where typically they have very low inversion barriers. So the typical inversion barriers you're dealing with are on the order of about 30 kcals per mole. So reasonably stable at room temperature. And so this chiral at P ligand family is an important, historically important class of ligands. They're often difficult to make in a modular way. I know the Baron Lab is working on this problem. And then, step over here. So then I'll draw out. Draw out now the depiction of the bonding to get a sense of the electronic considerations. And then after this, we'll jump into Day number 2, which builds on things we've already learned. And so we've seen before that phosphines are sigma donating, so that means they can donate the lone pair of the phosphine. Donate into an unfilled orbital of the appropriate symmetry on the metal. So let's consider this as the dx squared minus y squared, for example. And we mentioned that they can also be pi accepting. But the nature of how they're pi accepting, the understanding of that has evolved a little bit over time. So initially, it was thought, so you can not write this down if you think it might confuse you. So this is sort of historically what people thought might be going on, was that the unfilled, or a filled d orbital on the metal of the appropriate symmetry could donate into the unfilled 3d orbital on phosphorus. But our modern understanding is that actually the bigger contributor, though this is perhaps a contributor, the bigger contributor is donation into the sigma star antibonding orbital of, okay, so let me draw just one of these. And if you want to think of this in terms of maybe a more detailed MO treatment, then in reality this back bonding is taking place to an antibonding orbital that is a combination of sigma star and 3D. And so I think as first approximation you can just think of it this way, and that's useful, but I'll sort of draw out the more accurate MO depiction now. Here I'm trying to draw this coming out of the plane. I'm not sure if I'm succeeding, but that's what I'm trying Okay, so it's obvious that phosphines are strong sigma donors. They also have important pi accepting properties. These, in terms of their pi accepting ability, when the R group is sp2 hybridized, it's a much better pi acceptor than when it's sp3 hybridized, and also when it's oxygen substituted, then it has improved pi accepting characteristics. So let's consider this this in a specific example now. Problem of the day number 2, which asks you to consider a series. Well, first just a head-to-head comparison of a nickel carbonyl to a phosphine-bound nickel carbonyl, and then asks you to consider a series of phosphine-bound nickel carbonyls and asks for predictions about CO stretching frequency. So let's first consider 2A. first for 2A, Hansol, what do you think? Okay, so Hansol is saying that when you add one phosphine, replace one CO with phosphine, now the phosphine is going to be much more electron donating than the carbonyl. Now the metal center should be more electron rich, should be able to donate, participate in enhanced back bonding. That should weaken the CO bond, and should it increase or decrease the stretching frequency? I didn't catch that. It should decrease the stretching frequency. Okay? Everybody get that? Okay, now let's consider 2B. So this is a series where, and there might be differences like within the family of alkyl, but let's just say in general, let's for aryl consider phenyl, for alkyl consider 2-butyl, and for alkoxy consider methoxy or phenoxy. The insights will be essentially the same. Okay, what do you think, Elena?
I think alkyl would increase the phenols.
Okay, so alkyl will be the lowest stretching frequency. And then what about between?
And then would go
Al-
down with alkoxy.
Okay. Does anybody get anything different? So let's just throw up some numbers. So these are the three that you were asked to consider, and the trend is as Elena described. And so you can tell that as you move down this row, these become better pi bond acceptors. And if you want to consider a really extreme case, trifluorophosphine is a very strong pi acceptor. Some people have claimed that it's as strong of a pi acceptor as CO. I'm not 100% sure about that, but suffice it to say it's a strong pi acceptor, and you can see that manifest in the CO stretching frequency. And these are actually from the classic review. Camera. And this brings us to our chemist of the day. Which I don't know if anyone wants to shout out any ideas. No, that's a good guess.
Tolman?
Tolman, yeah. Right on. Okay. Chadwick is his first name. He was educated as undergraduate at MIT and then UC Berkeley, and did most of his research at DuPont. As you can probably have a sense for at this point, this was really in the heyday of organometallic chemistry at DuPont. Amazing stuff there. And he's famous for being one of the early pioneers in parameterization of phosphine ligands. That includes electronic parameterization, as you've seen here. So this is actually a ChemRev from Tolman. And perhaps even more famous for the Tolman cone angle, which we'll come to next. And so I think the really key insight that Tolman had and others at this time were also thinking about is that as you move from one phosphine to the next, there are structurally, especially for symmetrically substituted phosphines, they're somewhat similar. Right? And so you can actually, because the overall structure is somewhat similar, you can ask questions about how to quantify their differences. Differences in terms of electronics, differences in terms of sterics, and actually from those quantified differences then make meaningful predictions about properties and reactivity. Okay, so let's define this cone angle. So originally, this was way before the advent of any kind of computer modeling. So to make these initial measurements, Tolman actually just made the ball and stick models. I think they had really good ball and stick models back then, and used a protractor and just measured this angle. And so this is very powerful, but it does have its drawbacks. So I think in the Hartwig textbook, the cone angle is described as an extremely important metric, but a flawed metric. And it's flawed for a couple of reasons. One is that it doesn't take into account conformational changes, and the other is that it doesn't deal well with unsymmetrical ligands. So when you have three substituents and they're all phenyl groups, then it's easy to make this measurement. But when one is a toluene group, for example, how do you make that measurement? They did it by averaging, essentially by averaging the scenario where it's three toluenes, but this is a little bit imprecise. And so there's another measurement that is a little more precise, but also a little bit less obvious, which is called solid angle. And this basically treats the metal as a point of light, and then asks a question about the shadow that's cast on a sphere surrounding the metal. And of course, if it casts a bigger shadow, then it has more of a steric presence. This is just the shadow area divided by the square of the radius. Okay, so now we'll take a look at problem of the day number 3. This is the most involved problem of the day. There's a lot going on here. We'll try to go through it as quickly as we can. These are 3 common ligands, and you're asked to think about a synthesis. And so the point of this exercise is to gain some familiarity with how phosphine ligands are made, and then also, if you happen to know it, the name of the ligand and the name of the inventor. as always, please feel free to bounce some ideas off of your neighbor. Okay, let's get started on A. Stephen, what do you think?
So if you go from tartaric acid, make the diol, and do carbazole.
Okay, so Stephen is recognizing the chiral pool starting material involved here, tartaric acid. And you're saying...
So protected.
Protect, okay. I'm going to do a couple steps in one here. So let's doubly protect and then reduce.
Reduce, and then convert to a halide or pseudohalide. And this carbazole.
And then you want to treat with what? Anything special?
I guess it would be
Pell
like
reaction? In a pal or something?
yeah.
And then you want to do our food sob. Let's see if I spell it right. That might be an embarrassment, so and you're saying you want to do the phosphine. Is that close? No? And this is, I can't remember, OR, is that right? Supposed to be?
Yeah, I think so.
Okay, any other ideas for this stuff?
Can you do a mix with the phosphine oxide?
Okay.
So don't appel it, just do it
With the phosphine oxide. Okay. So we want to, yeah. Yeah.
For carbazole, isn't it tri-alkyl phosphine oxide?
Trialkyl. Yeah, okay. So then another, so it's another thing people will just commonly take. SN2 reaction. Good. Okay. And does anyone know the name or inventor of this very famous ligand and asymmetric catalysis? Tattle. No. Sean.
Can you adjust the camera? We can't see it.
Okay. Any other guesses? Who said? Oh, good. Okay. Yes, thank you.
In the future, you guys can also sit closer to the board.
And the inventor?
Suggestions.
Yeah.
I guess maybe the Lord.
Oh. I think Kagan would not be happy with that answer. Kagan. This was the first ligand that was working really well in asymmetric hydrogenation. So Kagan won the Wolf Prize for basically discovery and application of diop, and then fell. And then others were acknowledged with the Nobel. So if you're interested in the original references.
They use the SM2 route, right?
Yeah. So for alkyl phosphines, normally SM2 with the other diaryl phosphine is a good bet. Okay, how about the second one? Any ideas? Schwan. Max Moore, any ideas to help Schwan?
Is there some way you can do a Friedel press to get the phosphorus, or not Friedel press, but electrophilic aromatic substitution?
To install to make the CP bond?
Yeah.
That's an interesting idea. I think it's a pretty. If you have the biaryl linkage in place, I would guess that Friedel-Crafts would give you go to the opposite side because of
So
steroids.
then can you couple on phosphorus onto the halide?
Yeah, I like that. So the first disconnection is to break the CP bond, put a halide there, and then how are you going to make that?
The biaryl.
So Max is saying he wants to do this. Here's the product. Coupling. Again. Say. Okay, so you want to start with this biaryl halide, and then how are you going to make this?
I mean, it would be a tough cross-coupling, but
So I've seen that cross-coupling work before. I don't know about if it can tolerate oxy substituents, but there's a Kumada
Okay.
coupling with the
Potentially cross-coupling.
You switch the polarity, make phosphorus electrophilic, pairing.
Phosphine. What would you want to do there?
PCl bond, and then CLI bond.
Oh, I see.
Or maybe you don't
yeah.
even need that.
Yeah, I see.
It's probably
But anyway, you still need to make this unit somehow.
Could you make the biaryl last?
Biaryl last. Not necessarily.
Well, if you just use electrophilic phosphorus and you have a nucleophilic aromatic ring, and you do Krauss or directed lithiation, you don't need a.
Oh yeah, but I'm saying so if you want to, so you'd still need to somehow make the biaryl unit. I think the biaryl unit is not going to be commercial, right?
Oh, the biaryl, yeah.
do an oxidative coupling.
Okay. So coupling to like aryl Grignards or something like that. Okay. Any other volunteers?
Ligand. You study from chiral desoxy, benzene, and bromination, and making benzene.
Benzene? I hear benzene. Okay, good. I like that. So almost all of the modern buckwald ligands, the more complicated ones, are made from some benzene process. And that's because I think benzene helps you form this extremely hindered. You adhesive of enzyme intermediate helps you overcome this very hindered coupling you need to. So you can add a Grignard across an enzyme. Depronate, make the enzyme, add a Grignard across, and then you can trap it with electrophilic halide. You could try to trap directly with electrophilic phosphorus as well. I think in terms of the overall process, they find that's not the best way to do it, but it's a reason to propose it. Okay, and so for the details of that, I think, does anyone want to, I'm sure the inventor is obvious. Well, okay. And what about the name of the ligand itself? No? Okay, one at a time. What was it? Something fast. Someone probably just said it. This is Brett Foss. This one's not a cat. And Brett Foss is I think the characteristic feature of Brett Foss is this methoxy group, which allows it to toggle. Okay, and we're running over, so we'll just quickly do the last one and finish up. Okay, the last one, anyone volunteer from the audience? I'll just kind of show the disconnections of this. Any volunteer? Luke, what do you think?
SM2 displacement.
Okay, I like that. Double SM2?
Yeah.
So we're going to then get back to some. In general, if you see these alkyl phosphines, a good way to go is do some kind of SM2. And so this will get us back to a 1,4-diol. And so you can think about making this a bunch of ways: memory reduction, CBS reduction, keto reductase, and plus some nucleophilic phosphorus equivalent. Double NM. So those are good disconnections. I think in practice what they have to do is they first make this, they add a phenyl dilithiated species into it, and then they have to treat the resulting phosphylane with another organolithium to generate a new lithiated phosphorus that can attack like a dimethylated 1,2-diol. And anybody know the name of this? This is methyl BPD, and the inventor is Burke. That's a DuPont, another DuPont connection. So there's a related family of ligands some of you will have seen before called DuPhos, and the Du there is from DuPont. You find that reference?
Yes, it's Jack's 1993. White
115?
Yeah, page 10,135.
Okay. Okay, so with the last, just if you indulge me for another minute or two, I'll just make a couple comments about carbenes. We're out of time. So carbenes, in general, the ones that are going to these are by far the most common in Catalysis. Also a family that's on the rise, and I'll mention it just because it involves some of our neighbors, are these ligands that are called CACs, invented by Guy Bertrand's group. Compared to NHCs, they're both stronger sigma donors. and stronger pi acceptors. And NHCs compared to phosphines are stronger sigma donors. They're like trialkyl phosphines on the extreme. They're stronger sigma donors and quite weak pi acceptors. So these have NHCs have they're like the strongest trans effect ligands, and the amount of back bonding has been the subject of debate. But in general, you can just see them and think they're really strong donors. And they're weaker pi acceptors. And then also slightly different than phosphine is that the NHC metal bond is so strong that it's almost never dissociates. And then there's one, as you might tell from based on the coordination mode, things like the cone angle are not the best descriptors of NHC because of the way that they coordinate. And so there's a metric that's useful here that's been popularized by Steve Nolan. And this is called the percent buried volume. This considers the metal as the center of the sphere, where the radius of the sphere is something like 3.5 angstroms, roughly, and then just calculates the amount of volume. And the advantage is that this works with non-symmetrical ligands. But the weakness it has is still conformation. And if you're interested in that, here's a review. You can compute percent varied volume using this free computer program that you can find in this review, ChemCom 2007. Okay, that's it for today. Sorry I went a few minutes over. Happy to answer any questions, and if you didn't already turn in your homework, please do so before class. We'll have those back to you graded by Friday.
No, Wednesday.
Sorry.
And
By Wednesday.
If you haven't submitted homework,